Let's study 10th standard ICSE Physics, Chapter 11, Calorimetry. Calorimetry relates to heat and the transfer of heat. So first we need to understand what is heat. It is a form of energy and is defined as the total internal energy of molecules constituting the body. It is an energy which flows from hot body to a cold body when they are kept in contact. Although there are many ways in which heat can be transferred, namely conduction, convection and radiation. So being in contact is not strictly a requirement for flow of heat. But when we say internal energy, what does it mean? All of us are familiar with these diagrammatic representation of three states of the matter, namely solid, liquid and gas. In solids we see that the interparticle space is minimum and the interparticle force of attraction or the intermolecular force of attraction is maximum. If you heat it, then the kinetic energy of the molecules will increase. You see, even in the solid state, the molecules or the particles do have a kinetic energy. They are not stationary. They are vibrating about their mean position. But they cannot move away from this fixed position. That's why they are rigid. However, they do have heat energy. Even ice has some heat energy. Imagine if you have ice, which is a solid, at 0 degrees Celsius. We can cool it to minus 20 or minus 200 degrees Celsius, isn't it? What does it mean when we say cool it further? It means we are removing heat away from it. That means it does have heat. And that heat is nothing but this internal energy of the molecules. Internal energy. We are not talking about the energy which is visible from the outside, like the potential energy of an object just because it is at a height, or the elastic potential energy because something is stretched, or the kinetic energy of a car because if it is in motion. No, heat energy is completely internal energy. These particles have kinetic energy because they are continuously moving. Not only that, they have an internal potential energy also because of the intermolecular force of attraction. The greater the distance between them, the more is that internal potential energy. So heat is the internal kinetic energy plus internal potential energy. This is actually what heat is all about. It is the energy of the molecules of a substance. And every object in the universe has heat energy. Even ice at minus 200 degrees Celsius has heat energy. The lowest possible temperature ever in the universe is around minus 273 degrees Celsius, which is equivalent to 0 Kelvin. That's the starting point of the Kelvin scale of temperature, which is the SI unit. No degree here. What this lowest temperature represents is zero heat, zero internal energy, and practically it's impossible for any object to reach this temperature. Yes, scientists have achieved temperatures very close to it, like a fraction of a Kelvin just above it, but not exactly 0 Kelvin, because it's not possible for any object to have zero internal energy. Whenever we heat a solid, the kinetic energy increases because the heat energy is getting transferred to these molecules. And as the kinetic energy increases, the intermolecular separation increases because they are now able to overcome the intermolecular forces of attraction. So the intermolecular forces of attraction have now become weak. Now it is a state called liquid. Now the molecules can move from their mean position. They can move away. They are free to slide over each other. However, in this state, there is some intermolecular force of attraction existing still significantly. That means their volume will remain fixed. For example, water. Water flows, it's a fluid, because the molecules can slide over each other, but they cannot escape from each other. That is, if you have 1 liter of water in a container, and if you pour it in some other vessel, it will still occupy the same volume. They have a surface, a free surface, a single free surface on top, and there's water entirely filling the container. But there is this free surface, and water molecules can't just escape it in the liquid form. So they have a fixed volume, but no fixed shape. unlike solids which have a fixed volume as well as a fixed shape. So liquids can flow, the molecules can slide over each other, but they cannot just escape from each other. The intermolecular space won't be too much, though it is greater than what it was in solid state. Now you heat it further. It will expand. Always expansion happens first. The intermolecular distance will increase as the kinetic energy of the molecules increases. This is something which happened in solids also when they were heated. First expansion happens and then melting happens. And now again expansion, and finally it will boil. Now the kinetic energy of the molecules is so high that they will just escape from each other. They are able to overcome the minuscule amount of intermolecular force of attraction which was left, and now nothing can stop them. They don't have a fixed volume. They can occupy the entire volume available to them. The intermolecular space is immense, and this is the gaseous state. So again, when you heat a solid, first it expands, then it melts into a liquid. Then if you continue heating the liquid, it expands, and then it boils to form a gas. And as you heat the gas, it expands as well. At very high temperature, there is a fourth state of matter called plasma state, but that is outside the scope of this chapter. In plasma state, the electrons are just knocked off the atoms. So you have a soup of the nuclei, positively charged nuclei, and the freely moving electrons. There are no atoms. It is totally made up of ions, and that is called the plasma state. Example, the stars, the sun, the atmosphere of the sun. The outermost layer of the sun is totally made up of plasma state. We have plasma on Earth as well in many devices and in many places, but it's not as common as solid, liquid, and gas. The reverse is also true. If you cool the gas, then the volume decreases, it shrinks. The intermolecular distance decreases and the intermolecular force of attraction starts increasing, and then it liquefies, it condenses to form a liquid. If you cool it further, it will contract further, and then it will solidify, it will freeze to form a solid. Note that there are few exceptions. For example, water, when cooled below 4 degrees Celsius, instead of contracting, it expands. That's an anomalous behavior of water. Also, liquids can convert into gas not just at the boiling point, but at any temperature below it as well. So, before it starts boiling, already some of the liquid would have converted into a gas by a process called evaporation, which is a surface phenomenon. That means the molecules on the surface may escape in the gaseous state at any temperature. However, that is a slow process compared to boiling, which quickly turns the entire liquid into gaseous state at the boiling point, which is a higher temperature. For example, the boiling point of water is 100 degrees Celsius at 1 atm. That is 1 atmospheric pressure. The normal atmospheric pressure at sea level, 760 millimeter of mercury. The pressure matters while stating the boiling point because the boiling point depends on the pressure. So now that you've understood the basics of heat and the interconversion of the states of matter, let's talk about the units of heat. Now, if you have 1 gram of pure water, 1 gram of pure water, which is at, let's say, 14.5 degrees Celsius. This is just a temperature decided conventionally. If you heat it such that its temperature increases by 1 degree Celsius, that is, it becomes exactly 15.5 degrees Celsius for 1 gram of water. So the amount of heat provided is called 1 calorie. So this is a unit of heat, although it is not the SI unit. The SI unit of heat energy is the same as the SI unit of any energy, joule. And 1 calorie is in fact equal to approximately 4.2 joule. So we need to learn this conversion. What about a kilocalorie? Well, if you have 1 kg of water and you heat it to convert it to increase the temperature by 1 degree Celsius, then we say that the heat provided is 1 kilocalorie, which will be equal to 4.2 into 1000 joule, of course. So that was about heat. But how is it different from temperature? Is it the same as heat, or is temperature a totally different physical quantity? Well, imagine that there is an object which is very hot, extremely hot. And there is another object which is quite cold. So this is hot to touch and cold to touch. This is hotter than this. But if I calculate the total heat energy in this, it is, let's say, 50 joule. And surprisingly, this one has 70 joule of heat energy. Yes, it's possible. So if they touch each other, will heat flow from 50 joule to 70 joule or from the hot object to the cold object? Well, the flow of heat energy depends on the temperature. It will always flow from a hot object to a cold object. So that is how temperature is totally different from heat. I said that the heat is the total internal kinetic energy and the total internal potential energy, whereas temperature only depends on the average kinetic energy. Temperature is actually a quantity which tells us what is the average kinetic energy of a substance. That is how fast the particles in that object are moving. That's what temperature tells us. It does not tell us about the internal potential energy. So temperature doesn't tell us entirely how much heat an object has. Now, surprising as it may be, you may wonder how come the hot object has less heat energy than this cold object. You can see, look at the size of this object. So it means that perhaps this has more mass. And yes, heat depends not only on temperature, but also on the mass of an object. So heat, let me call it Q, is actually the product of mass, specific heat capacity, which depends on the material being used. I will define this very soon. And also the temperature or the change in temperature. So the heat depends on three factors: the mass of an object, the specific heat capacity, and the temperature. We will study this in detail soon, but right now I want to focus on temperature. I want to show you how temperature is different from heat. Yes, temperature does affect heat, amount of heat energy, and heat, it depends on the temperature, but they are not the same thing. Temperature only defines the average kinetic energy. It just determines the direction of flow of heat. It tells us in which direction will the overall heat energy flow. And obviously, the heat will keep flowing till both of them have the same temperature in the end. That is called equilibrium, thermal equilibrium. And even if they are in equilibrium, the same temperature, doesn't mean that they will have the same heat energy. No. For example, if you have a bucket filled with water which is at 30 degrees Celsius and a swimming pool full of water at 30 degrees Celsius, do you think that the heat energy in both is same? No, it isn't. Because the swimming pool has more mass. Even though the temperature is same, and even the specific heat capacity is same, because both of them are just water, same material, but the masses are different, and more the mass, more is the total heat energy in that substance. It's like this. Take let's say Sri Lanka and India. Let's say the per capita income of Sri Lanka is $1,000. I'm just taking some random figure. $1,000 per capita income. Means per person has an income of $1,000 annually. And even in India, let's say that per capita income is $1,000 income per person per year. So both of them have the same per capita income. And yet, India's GDP or the total income of India is more than that of Sri Lanka. Why is that? The total tax collected by the Indian government is much more than the total tax collected in the Sri Lankan government, by the Sri Lankan government. Why is that? Even if the tax rates are same, it's because there are more people in India. So if you multiply the number of people with the income per person, the total GDP, the national income, is far greater. Similarly, even if the temperature is same between a swimming pool and a bucket full of water, there are more water molecules in a swimming pool, so the total heat energy is more there. So clearly, more the mass, more the heat energy. That is why if you were to heat just 1 gram of water and increase the temperature by 1 degree Celsius, you require very less heat. It would happen very quickly. Now you take 1,000 gallon of water, or say 1,000 liters of water, which will be, let's say, 1,000 kilogram of water, and now try to heat it by just 1 degree Celsius. You'll require a lot of heat. Even though we want to increase its temperature only by 1 degree Celsius, it requires a lot of heat. So clearly, heat depends on mass. And of course, temperature also will affect heat. If you want to increase the temperature by 1 degree Celsius, you'll require some heat. But if you want to increase it by 10 degrees Celsius, you will require more heat, assuming that the mass is same. So clearly, more the temperature increment, more is the heat required. And temperature, as I said, SI unit is Kelvin, And how to convert degree Celsius to Kelvin? Well, just add 273. And how to convert Kelvin to Celsius? Subtract 273. But what is this third quantity? C. Before I talk about it, there is one more point I would like to discuss. If I were to mix these two buckets of water, 50 joule plus 70 joule, then the total water will have a 120 joule of heat energy. So heat can be added like this. But if you have an object which is at 40 degrees Celsius and the other object is at, let's say, 20 degrees Celsius, if you mix them, what will be the new temperature of this mixed water? Will it be 40 plus 20, 60 degrees Celsius? No. Will it be the average of the two, let's say 30 degrees Celsius? Not quite, because the masses are different. I guess it will be more towards 20 and far away from 40, let's say 25 or something. It depends on the mass. So you see, temperatures cannot be added arithmetically like heat can. So these were the differences between heat and temperature. And now finally, talking about C, the specific heat capacity. If I give you 1 gram of water and I tell you to heat it by 1 degree Celsius, you would say that it required so and so calories, let's say 1 calorie. And it took 1 minute. Next, I give you oil. Again, 1 gram, exactly 1 gram, same mass. And even its temperature needs to be increased by 1 degree Celsius, say 14.5 to 15.5. Again, 1 degree Celsius. But you will notice that oil heats up very fast compared to water. It took just half a minute. Maybe just, let's say, half a calorie. So less heat was required. But the mass was same. The temperature was same. And yet the amount of heat required differed. That means the material of the object also matters as far as heat is concerned, and that is the specific heat capacity of a substance. So when I say that for 1 gram of water, to increase its temperature by 1 degree Celsius or 1 Kelvin, 1 Kelvin and 1 degree Celsius are the same thing, because if the temperature increases by 1 degree Celsius, I can even say that it increased by 1 Kelvin. So the heat required here is called the specific heat capacity of water, which is 4.2 joule per gram per Kelvin. 4.2 joule per gram per Kelvin. That is the specific heat capacity of water. In SI unit, it will be 4200 joule per kg per Kelvin. But if I take 1 gram of oil and to increase its temperature by 1 Kelvin, if the heat required is, let's say, just 2 joule, then I say the specific heat capacity of oil is equal to 2 joule per gram per Kelvin. This is specific heat capacity of water. This is specific heat capacity of oil. So what is the meaning of specific heat capacity? Well, it means if you take 1 gram of any object and if you want to increase its temperature by 1 Kelvin, how much heat is required? That is the specific heat capacity. That's an inherent property of that substance. Like density. Density of copper is fixed. Resistivity of copper is fixed, or the refractive index of glass is fixed. Similarly, the specific heat capacity of an object, a pure object, is fixed. It has a fixed value. And there's a table which you can use to find out which has the highest specific heat capacity. You can see water has unusually very high specific heat capacity. What it means is, if you give me 1 kg of water and you want me to increase its temperature by 1 Kelvin or 1 degree Celsius, I will need to give it 4180 joule of heat energy. That's a lot. It means heating up water is not an easy task. You will have to give it a lot of heat. This has some consequences. On the other hand, metals, good conductors of heat, like mercury, etc. Look at how easy it is to raise their temperature. How easy it is to heat them up. A little bit of heat and their temperature increases, just skyrockets. By the way, the substance with the maximum specific heat capacity is hydrogen. It's much more than water. So specific heat capacity does not depend on the mass of a substance. If you ask me what is the specific heat capacity of water in that bucket, I would say 4.2 joule per gram per Kelvin. Or if you ask me what is the specific heat capacity of water in that swimming pool, assuming it's pure water, again I would say 4.2 joule per gram per Kelvin. So the value remains fixed. It does not depend on the mass of the object. However, if you change the question and if you ask me, here's a bucket of water, how much heat will be required to raise its temperature by 1 degree Celsius? I'll calculate, and we will do such calculations when we do numericals. Let's say I will say the answer is 200 joule. And now you ask, how much heat is required to raise the temperature of the entire swimming pool of water by 1 degree Celsius. Now again, after calculation, perhaps I'll get an answer like 20,000 joule. Obviously, I'll require a lot of heat to heat up the swimming pool, even if it's just 1 degree Celsius. But look at the mass of that pool. Require a lot of energy. So what I'm calculating now is called heat capacity, capital C. Specific heat capacity was the amount of heat required per gram per Kelvin. But heat capacity is the amount of heat required per Kelvin. Here, mass is not there in the unit because it will depend on the mass. So the heat capacity of the bucket full of water is less, but the heat capacity of the swimming pool full of water is more because this has more mass. So the relationship between heat capacity and specific heat capacity is that heat capacity is equal to specific heat capacity multiplied by mass. That's the relationship between heat capacity and specific heat capacity. Specific means per gram or per kg. And if I just say heat capacity, I mean no matter what mass of water or any substance you give me, I will calculate how much heat is required to raise its temperature by 1 degree Celsius. The units are also different here. It's joule per Kelvin and here it's joule per gram per Kelvin. And this makes sense, you know. Look at this equation. Heat is equal to mCp. If I rearrange it, I'm getting specific heat capacity is equal to the heat upon mass into temperature. Heat is joule, mass is kg, and temperature is Kelvin. So joule per kg per Kelvin. We can also write like joule, kg inverse, Kelvin inverse. And this is the SI unit of specific heat capacity. Next, let's understand calorimeter. Draw this diagram for homework. What if I want to calculate the specific heat capacity of an object? The method I'm going to use is, what if I put a hot copper ball in cold water? Then I can say the heat lost by copper is equal to the heat gained by water. You know, assuming there is no loss of heat energy, all the heat lost by the copper ball will be equal to the heat gained by water. And the copper ball will cool down, water will heat up, till the time both of them have the same temperature. Let's say copper's initial temperature was 80 degrees Celsius and water's initial temperature was 20 degrees Celsius. And the final temperature they reached when I mixed them together was, let's say, 30 degrees Celsius. So copper cooled down to 30 and water heated up to 30. That's the final temperature for both, of course. Now heat formula is mass into specific heat capacity into change in temperature. Here masses of copper, of course, copper, and T1. And heat, again, formula is mass of water into specific heat capacity of water and change in temperature. Let's say the copper's mass was 2 grams. And the specific heat capacity of copper is something I have to still calculate using this experiment. Temperature difference. What is the difference in temperature? 50 degrees Celsius. No need to convert it to Kelvin because when I say 50 degrees Celsius, it means a difference of 50 Kelvin also. Mass of water, let's assume that it was 10 gram. Specific heat capacity of water is 4.2 joule per gram per degree Celsius. Or if you take it in terms of calorie, then you'll get the final answer in calorie. But let's stick to 4.2 joule. Notice that this is gram, hence I took 4.2. If it was kilogram, then I would have taken this as 4,200. And what's the difference in temperature here? 10. Okay, 10. So now let me calculate the value of specific heat capacity of copper. Well, surprisingly, I got the same answer as water's specific heat capacity. See, these are just random values. But the answer I got is 4.2 joule per gram per degree Celsius. By the way, this is not the SI unit. SI unit is joule per kg per Kelvin here. So the SI unit answer would have been 4,200 joule per kg per Kelvin. So this specific heat capacity of copper is useful. It helps us to understand how good a conductor of heat it is, how much heat energy would it be required to heat anything made up of copper, etc. So now you understood the use of this formula. This is the principle of calorimetry. Heat lost is equal to heat gained. Here there's a big assumption that there's no loss of heat. But when I do this experiment, How do I ensure that there is minimum loss of heat energy? Well, for that, we use calorimeter. There's a thermometer so that we can measure the starting and the final temperatures. We have a stirrer to stir the solution, that is a water. A wooden lid, a wooden jacket, because wood is a bad conductor of heat, preventing loss of heat. Inside we have a copper vessel. Copper is a good conductor of heat and it has a very low specific heat capacity, so it will attain the temperature of the water very quickly without absorbing much of the heat. There is wool filling out here. Again, this will prevent the loss of heat energy. The outer and the inner surfaces of the vessel are polished. They're very shiny, so that any rays, any radiations from outside or inside are reflected back, and there is no loss of heat due to radiation. Conduction and convection are also avoided with the help of the poor conductors like wool, cotton and wood. And why are we using copper? I've already said that because it has a low specific heat capacity. So if the water is at 20 degrees Celsius or 40 degrees Celsius or 60 degrees Celsius, the copper container will also reach that temperature very quickly without absorbing much heat. The mathematical statement is similar to what I had written, that heat energy lost is equal to heat energy gained. So M1C1 T1 minus T is M2C2 T minus T2. Remember, T is the final temperature, which is the same in LHS RHS. T1 and T2 obviously are different temperatures. You saw that here, this was T1 and this was T2 and this was T. So we'll do a lot of numericals with these formulae. In fact, in some numericals we'll use this formula because let's say this is the heat lost by copper ball and this is the heat gained by water. But what about the heat gained by the copper vessel, the calorimeter? Even that should be taken into account, isn't it? So if that information is given in the question, that data is given, then we will use this formula. Now, the fact that water has a very high specific heat capacity has some amazing consequences, and these are very important give reasons. Before that, I would like to stress that the principle of calorimetry, also called principle of method of mixtures, is based on the law of conservation of energy. Now, why is the climate near the seashore moderate? You will notice that Mumbai has moderate climate compared to Pune. Mumbai is a coastal city and Pune is just a few hundred kilometers away, but Pune experiences extremely cold winters and extremely hot summers. Mumbai also has cold and hot weathers, but the difference in the temperature is not as extreme as it is there in Pune. That's because of the proximity to the sea, because of the Arabian Sea being close by, and water near Mumbai, it has a very high specific heat capacity. That means it can absorb a lot of heat. It has a capacity of absorbing a lot of heat. So during summer, the temperature of the seawater doesn't rise very quickly. And during winter, the temperature of the seawater doesn't fall very quickly. You must have studied about land breeze and sea breeze in geography. This is land and this is the sea. So during the daytime or during summertime, for that matter, the sand becomes hot very quickly, whereas the water takes its own sweet time to heat up. You see, for 1 gram of water to raise its temperature by 1 degree Celsius, it requires 4.2 joule of heat energy. And sand would do it with 1/5 that heat energy. Anyway, so the temperature of the air above water is less. There's cool air out here and there is warm air out here. And air always blows from high pressure to low pressure. Warm air rises, its density is less. Cool air is heavier. So we have something called the sea breeze. The cool breeze keeps this coastal area cool comparatively. Compared to, let's say, an area which is far away from the sea coast, that will become warm and hot very quickly. At night or during winter, the opposite happens. So again, this is the land and this is the sea or the ocean. So at night, the land becomes cool very quickly and so does the air above it due to conduction. Whereas the water, which had been absorbing heat throughout the day and reach some high temperature, will take again a lot of time to cool down because of its high specific heat capacity. So the air above it is warmer comparatively. So now this rises up and the cool air blows. So this is called land breeze. So the warm air rises and takes its place here, making this area warmer than it would have been otherwise. A faraway place would become very cold at night. So this is called the moderating influence of the sea. Similarly, when you do fermentation, you may have seen such rubber bags or plastic bags which have hot water inside them. It gives you relief from muscle pain. That is called fermentation. Why is water used inside them? Same reason, water has a very high specific heat capacity. That means once you heat water, it takes a lot of time for it to cool down. For a very long time, it will give heat, which is what we want during fermentation. It's the same reason why water is used as an effective coolant. For example, in any machine or in an engine of a car, water can be used because water has the ability to absorb a lot of heat without raising its temperature much. Fourth GR, in cold countries, water is used as a heat reservoir for wine and juice bottles to avoid their freezing. So in their wine cellar, they have buckets filled with water and they have wine bottles in them. Why are they kept in water? Because if it's freezing cold outside, the alcohol might freeze. To prevent that, let's keep it in water, because water is a reservoir of heat. To decrease the temperature of 1 kg of water by just 1 degree Celsius, it has to lose 4,200 joule of heat. That's a lot. It won't cool down so quickly. It has a lot of heat stored in it. That warmth will be enough to prevent the alcohol from freezing. This is also the reason why farmers fill their fields with water to protect the crops from frost. If they come to know that the night temperatures are going to fall below 0 degrees Celsius, they quickly flood it with some water. So that for those few hours at night, the water, which is a reservoir of heat, it has a high specific heat capacity. Remember these key words in your answers. They will prevent the freezing of the water in the veins of the plants, in the xylem vessels of the plant leaves and roots. Because if they freeze, the plant will die. All plants and animals have a high content of water in their bodies. That's right. Your body is around 80% water. Some of you have brains which are almost 99% water. Looking at your answer sheets. So why do we have so much water? Well, to maintain a nearly constant temperature of a body in all seasons. Now, let's talk about something else apart from water. There are some substances which have a very low specific heat capacity, like metals. Why is the base of a cooking pan made thick? That's because if it is thin, it won't have a high specific heat capacity. We want to increase the specific heat capacity. So the cooking pan's base is made thick. More the mass, more heat capacity. I'm talking about heat capacity and not specific heat capacity. What it means is that it will take time to heat such a thick base of a cooking pan. But once you heat it, then you switch off the gas, it will remain hot for a long time. It will keep the food inside it warm for a long time. Similarly, the base of an electric press, electric iron, is also thick and heavy, so that it will remain hot for a long time even after you switch it off. On the other hand, the calorimeters are made up of thin sheets of copper because we wanted to have low specific heat capacity, which we've already discussed. Now let's talk about interconversion of state of matter. Now we should not call it state of matter, we should call it phase of matter. It sounds fancy, but hey, you're a science student now. Draw this diagram. I know you've been doing it since kindergarten. Learn all these definitions. Solidification. Sublimation, of course, is a change of state from solid to gas directly without passing through the liquid phase. The intermolecular attraction between these friendly molecules is so weak that a little bit of rumor and they just become enemies and go wide apart and they become gas. That's sublimation. Can you give me an example of sublimation? That's right. Naphthalene, camphor, iodine, ammonium chloride, dry ice. Learn the definition of melting, freezing. Remember that the change of state always happens at a fixed temperature. Let's take an example. I have ice at, let's say, minus 5 degrees Celsius. Ice. I start heating it. Obviously, its temperature will rise and rise and it will become 0 degrees Celsius. And I'm checking it with the help of a thermometer. But surprisingly, now if I continue heating it, its temperature doesn't rise anymore. It stays constant at 0 degrees Celsius. What I do see is happening is the ice is getting converted to water at 0 degrees Celsius, which is the melting point of ice. And only once the entire ice has been melted into water, then if I continue heating it, its temperature will continue rising to 10, 20, 30 and so on. So whatever heat I was providing for those few minutes, it was not being used to increase the temperature. It was being used to change the state of matter. It was not being used to increase the kinetic energy. It was used to increase the internal potential energy, that is increasing the intermolecular spaces. So this hidden heat is called latent heat, and here it's melting, so it's called latent heat of melting or latent heat of fusion. The same thing would happen during boiling also. Suppose the liquid was at 50 degrees Celsius, you heat it, it expands, it warms up to 90 and finally 100 degrees Celsius. But if you continue heating it, its temperature won't rise, it will stay at 100 degrees Celsius, but now it is getting converted from liquid state to gaseous state. And only after it has completely become water vapor or steam, now if you continue heating that gaseous state, now its temperature will start increasing further. So what happened in between? Well, the heat was being used not to change the temperature, but to change the state of matter. That is called latent heat, and now it's called latent heat of vaporization or latent heat of boiling. Because this heat was used not to change the temperature, that is not to change the internal kinetic energy, but to increase the internal potential energy. So now you know what is latent heat. If we were to draw a graph, you would notice that for some time the temperature remains constant at 0 degrees Celsius, and only then after the melting is over, then the temperature starts rising of water. This is called the heating curve. Even here, initially the liquid increase its temperature 20 to 100 degrees Celsius, but after that, after 100 degrees Celsius, even if you continue heating it, its temperature doesn't rise further. It's a flat line. This is the boiling point of water, 100 degrees Celsius. And till the time all the water hasn't boiled, its temperature won't increase because a change of state is happening right now. This is the latent heat again. By the way, a melting point is affected by pressure. The melting point of ice decreases when the pressure increases. This is an exception for ice because of anomalous expansion. Otherwise, normally the melting point of any substance increases when the pressure also increases. You see, if the pressure on that object is a lot, it becomes more difficult to melt it. You require more heat to melt it. A higher temperature is required to melt it. Even impurities can affect melting point. In case of water and most substances, the freezing point, the melting point decreases because of impurities. If you add salt to ice, its melting point becomes minus 22 degrees Celsius. So such a mixture is called a freezing mixture, which is used for preparing kulfis. Often you've seen those earthen pots in which kulfis are kept in a mold. Sometimes those sweet ice creams may have a little bit of salty taste. That's because of the surrounding ice which has salt in it. They would prevent the melting of the kulfis, keeping the temperature very low. There are many definitions which we need to learn here. Even the boiling point is affected by pressure. As the pressure increases, the boiling point increases and vice versa. Again, the same reason, if there's a lot of pressure on water, it's difficult for it to boil. It's difficult for it to expand and escape. You'll require a lot of heat energy, a higher boiling point to convert it from liquid to a gas. That is why on top of a mountain, the boiling point of water is not 100 degrees Celsius. It's lower. It's around, let's say 70, 75 degrees Celsius. So boiling water becomes very difficult or very easy, and cooking becomes very difficult at high altitudes. The solution is to use pressure cookers to cook. Even at sea level, we can use pressure cooker. Steam is not allowed to escape from it. That means the pressure inside becomes very high, due to which the boiling point of water increases to around 120 degrees Celsius. So water remains in liquid state inside. This is very efficient as far as cooking is concerned. Water is not wasted much, fuel is saved, time is saved, and what food is cooked properly. Impurities also affect the boiling point. If salt is added to water, the boiling point increases. That is why while cooking, if you remember, salt is added to the water. So we know that the hidden heat, which is used not to change the temperature, but to change the state of matter, is called latent heat. So if you give me, let's say, a bucket full of ice, here, let's say 10 kg of ice, and it's at 0 degrees Celsius, and you want me to melt it, again, to 0 degrees Celsius of water. The temperature has not changed. The heat being used to change the state of matter is called latent heat. Let's say I'm using 500 joule of heat energy here. So what is the latent heat of this ice? 500 joule, because that's the heat required to melt it without changing the temperature. But this was for how many kg did I say? I guess 10 kg. I guess 10 kg. So what is the latent heat per kg? That's right, it's 50 joule per kg. That means every kg of ice at 0 degrees Celsius requires 50 joule of heat energy to melt it. Please note there is no change in temperature, so no need to write per Kelvin here. It's latent heat, not specific heat capacity. Specific heat capacity is used when there is a change in temperature. Latent heat is used when there is no change in temperature but a change in state. Please remember this point because in numericals this is very vital to understand. So this is called specific latent heat. Again, when I say specific, I mean per gram or per kg. For water, again, it has a very special property. It has a high specific latent heat of fusion. To melt 1 gram of ice at 0 degrees Celsius, of course, you need 336 joule. Or to melt 1 kg of ice, you need 336,000 joule. That's quite a lot. Ice does not melt so easily as some other solids. And there are some consequences of this high latent heat of fusion of ice. In fact, the water has high latent heat of vaporization also. Boiling water is also not so easy, but that is not in our syllabus. So let's talk about the consequences of high specific latent heat of fusion of ice. First of all, the explanation of latent heat on the basis of kinetic energy and kinetic model I've already explained. Now, snow on mountains do not melt all at once. How come the Alps or the Himalayas have snow for a very long time? Even if the sun is up, it's noon time, you hardly see the ice melting. Well, partially the reason is the high specific latent heat of fusion of ice. To melt even 1 kg of ice, you need 336,000 joule of heat energy. So it melts very slowly. And secondly, the reason is that snow reflects most of the light, so it doesn't absorb much of it. In cold countries, water in lakes and ponds do not freeze all at once. It takes a lot of time for it to freeze. Same reason. Water has a high specific latent heat of fusion, which is 336 joule per gram. This is the opening sentence for all these give reasons. You have to learn this sentence and use it in every give reason based on latent heat. What this means is that if you want 1 gram of ice to melt, it will have to release 336 joule of heat energy. But if a lake is already covered with an ice sheet on top, then how will the water below it freeze? Because ice is a bad conductor of heat. The heat it wants to lose to the environment will be blocked by this ice sheet, keeping the water warmer under it. Now, one very interesting give reason. If you have a cold drink and you want to cool it quickly, which one will cool it faster? If you add ice cubes at 0 degrees Celsius or if you add some water at 0 degrees Celsius? The temperature is same, but will the cooling effect be same? Well, the ice will cool it faster. Because when the ice will melt, 1 gram of ice will absorb 336 joule of heat energy extra compared to this water. This water is already molten. It does not absorb any latent heat, whereas ice will absorb a latent heat. So it will cool this cold drink faster. Similar reason why if you get burns because of boiling water at 100 degrees Celsius or steam at 100 degrees Celsius, which is more dangerous? Well, it will be steam at 100 degrees Celsius because the steam at 100 degrees Celsius has more heat compared to water at 100 degrees Celsius because steam also has latent heat extra, which water doesn't. When the ice in a frozen lake starts melting, why does the surrounding become very cold when the lake melts? You see, if the lake is melting, that is, the ice is melting, the frozen lake is melting and the ice is melting, it is absorbing the heat from the surroundings. And if it absorbs all the heat from the surroundings will lose heat, so the surroundings become cold. That is also the reason why after the hailstorm, the weather becomes cooler. During the hailstorm, it doesn't become so cold as compared to what happens after the hailstorm. Because after the hailstorm, hails are, the big balls of stone-like ice. It's a type of precipitation. So when the hails melt, they absorb a lot of heat from the surrounding air, and so the environment becomes very cold.
Hi students, this is AJ sir. If you like this video, press the like button. If you would like to enroll for my online test series or online lectures, email me or message me on Instagram. Check the description for more information.